Jascha is one of the great geometers of our time, and he truly deserves this recognition. He has been working in this field for maybe 30 years, both creating it and then driving it and then solving a lot of important problems. Contact and symplectic topology is a part of geometry that grew out of classical mechanics. So when you have a mechanical system, you typically want to describe it maybe like the positions and the speeds of the different particles, but sometimes you can be smart about it and choose some other coordinates like angles or something like that, and the system becomes simpler. So in physics you think what kind of properties of this system are actually preserved if you change coordinates and so on. And out of such questions grew the area of contact and symplectic geometry. In mathematical language, rigidity belongs in some sense to geometry, the geometry that we know from high school or wherever, and flexibility is rather belonging to a branch of mathematics called topology, which is very near the two. So maybe one can illustrate by a very simple example. So if you take a stick, a rigid stick, and then you want to measure it, you can take your little centimeter stick and you put it and you count how many times, how many such sticks you can fit in the big stick. And if you can fit, say, 5 in one stick and then 7 in another, then the objects are different. So you cannot transform one to the other because they're rigid. Now if we move to the flexible region, we should imagine the stick being made of a very flexible material. So you can stretch it to any length you want. So you can fit the 7 centimeter sticks or 3 or 2, so they're all the same. And Jascha has been working on both sides and proving surprising results that things that you wouldn't expect are flexible or actually flexible, and also ways to measure rigidity. As another illustration of rigidity phenomena, you can actually use knots or knot theory. So in order to imagine a knot, you should imagine a kind of piece of spaghetti that you throw up in the air. Actually, you have to tie it to itself, so it's a closed spaghetti. You throw up in the air and then you freeze it. So that's a knot, and it can be knotted in various ways. In particular, there are those knots which obviously, if you imagine them as being used of ordinary spaghetti, you can deform one to the other, but if you put on the contact condition, then you cannot. And the development of Jascha was somehow to find the right way of counting the kind of small centimeter pieces to show that actually in this knot you can fit 7 of them, and in this one you can fit 5, and therefore they are different. So the use of this has been an interesting spread, I would say, in mathematics. So it made the symplectic geometry and contact geometry in a more central field of mathematics with close ties to many other fields like low-dimensional topology, complex analysis, and also lately to high-energy physics with the field of quantum field theory and string theory. So it became a very central subject, I would say, in mathematics.